right, so in this lecture, I want to look at the properties of amides. Whoop, I lost my, there we go. So we're going to look at the physical, just briefly, and chemical properties of amides. Okay, so the first is looking at the physical properties of amides. In particular, we're going to focus on the things that are more pertinent to the things we've been talking about in this class. And that is, I want to talk about the nature of the CN bond. So I'm going to talk about the nature of this bond. Now, it turns out that DMF, a common solvent, and that stands for dimethyl formamide, all right, so in structure, we have a formamide, which means we have a formyl group attached to a nitrogen. Now, the dimethyl corresponds to the groups attached to the nitrogen. DMF has two methyl groups. Now, both of these methyl groups have different or exist in different chemical environments according to NMR. That's weird because if we look at those two methyl groups, they don't look like they should necessarily be in separate chemical environments, right? They're just two methyl groups attached to the same element. Look like they should be in the same chemical environment, so they should have just one signal. But we have two signals here. Why is that? What in the world is going on with these two methyl groups? Well, it turns out that we can consider the resonance structures of amides to get to some important considerations when we're looking at an amide, resonance structures of amides. Okay, the first is if we look at this structure, we want to consider a resonance structure. The first one I would go to is one in which the carbonyl has charge separation. There's a negative on the oxygen and a positive on the carbon. Okay, but if you recall from resonance structure, the resonance structure lab, we wanted to look at a resonance structure where the lone pair from nitrogen could come over and neutralize the positive charge on that carbon. It turns out that that is a better resonance depiction than the middle resonance structure. Obviously, it's best to have no charge separation, but if you look in this other resonance structure, everything has an octet. So everything has an octet and it's all happy. So I would call this first one the best and this next one the second best. And I guess that middle one among the three is the worst, but I don't want to attach worse to that because you could draw worse or lesser contributing resonance structures. Okay. So what this does is this showcases some important properties about dimethyl formamide. Namely, there's double bond character at that C end position, at that CN bond. And if we have double bond character, we have restricted free rotation. So we always say no free rotation at double bonded systems, right? Because we don't have pi overlap. We can't maintain the pi bond when things rotate. We've said that since organic 1. In reality, what it is it's restricted free rotation, because if you've got a double bond present, that just sort of increases the barrier to rotating. It is possible supplying enough energy to rotate that bond. You have to break the pi bond, introduce diradical, blah, 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 blah. Anyway, there's just a barrier to the process that's higher than a typical free rotation about a single bond. Now, in this case, we see an increased barrier to the free rotation over that carbon-nitrogen bonded system. And we can account for that by looking at a resonance structure where we see double bond character between the carbon and the nitrogen. Additionally, what I want to point out about the nitrogen is the nitrogen actually is sp2 hybridized. And we could see that from this resonance structure, even though in the original structure, we see we have a lone pair attached to three other things. So it starts to look sp3-like. I won't go into it too much. I'll just say it's actually quite planar. That is, if this structure is sp2 hybridized, it's planar. The nitrogen is planar. It's not taking its lone pair and like pushing some things down to make a pyramidal geometry. It's quite planar. That's what I want you to focus on, is the double bond character between the CN and the planarity of the nitrogen atom that in this depiction, or whatever, is just bonded to the carbonyl carbon. Okay, if you've got double bond rotation if you have double bond character and restricted free rotation about the CN bond, then what that means is the alternative depiction of the exact same molecule, that is this resonance structure, also has restricted free rotation about that carbon-nitrogen bond. It's just a different depiction of the same molecule. Just these different depictions can give us insights into the real properties and help us explain why this methyl group on top is often close to the CO double bond. What I mean by close is that the methyl group down here is often far from the CO double bond. We've slowed the free rotation. And on the NMR timescale, NMR having a shutter speed, we can't blur the two together like we could with a normal free rotation. And so what we see is that since one is close and one is far, these two have different 1H NMR chemical shifts. So we see three signals in the 1H NMR of DMF that go 1 to 3 to 3 integration. We've got our one hydrogen here. We have a 3 hydrogen methyl group here and a 3 hydrogen methyl group here. Maybe that's a good exercise for us to do in lab sometime towards the end of the semester. I always struggle with an amide lab. So maybe like something with DMF and the NMR properties would be useful. Okay, so that's what I wanted to mention in terms of the properties, the physical sort of properties. Let's get into the chemical properties of amides. So the chemical properties of amides is just, another word would be the reactions of amides. All right, exciting stuff, right? Well, let's remind ourselves that amides are mostly unreactive. Amides are mostly unreactive. Bummer, right? So we're not going to see too many interesting things happen here, but we can do a few things. So the first thing I want to mention is the reduction of amides. All right, so reductions of carboxylic acid derivatives. We haven't talked too much about this, but now's as good of time as ever. Let's take our amide and we're going to add a good reducing agent like NaBH4. All right, we do the reaction and nothing happens. Bummer, right? So we tried to do a reaction where we added 2 hydrogens, an H- and then an H+ across the system, but we see no reaction. Now, what about a more reactive reducing agent like lithium aluminum hydride? Ooh, actually here we do see a reaction. In this case, we convert our amide into an amine. Spelling is critical there for that functional group. And we did so by adding the H4 reducing hydrogen atoms to the position that was the carbonyl group. Well, that's pretty cool. Okay, so what does that reaction look like? Mechanism for amide reduction looks like this. We're going to take our amide and we're going to consider it as a resonance structure. Not the best resonance structure here, not even the second best one. It allows us to see we have positive charge character in some depictions of this at that carbonyl carbon. And so we can add our H minus, which is from lithium aluminum hydride, to the carbonyl carbon. This could be shown in either of these resonance structures. You could even show it in that second best resonance structure. If you wanted to, because we have positive character on the nitrogen, so we would add to the carbonyl carbon and push electrons into the nitrogen. Any resonance depiction will do the same reaction. You just need more arrows. Okay, so we're going to do an addition reaction of a nucleophile. And no matter which resonance depiction you consider, you should end up with this structure at the end, where the H minus that adds is now in this position. Okay. So what we do at this stage is we have to recognize that the negative charge is going to add up to something on our system. And that something is going to be an AlH, and I'm going to put in trihydroaluminum. So the negative charge is going to add up to the group 3 element on aluminum to give us this intermediate. Now this intermediate, while it's negative on the aluminum, is not very stable. What will likely happen is an H minus could be lost to another reduction reaction. I'm just going to do this. Okay, so we're at H2 and then we're neutral. Okay, what we need to focus on though is the lone pair on the nitrogen coming down to push off the oxygen as a reasonable leaving group when it's adducted to a Lewis acidic element like aluminum. This is an elimination step that helps to culminate our addition elimination sequence. And when we do this, we get an aminium species that can react with another hydride nucleophile from the lithium aluminum hydride to give us our product. So there's the next hydrogen that has added to the system. And I guess here was the first one. So we added 2 hydrogens, both of which come from the lithium aluminum hydride. It's just that the process involves first an addition elimination to make an imine, and then the imine gets reduced, or aminium species. So we start with addition elimination, and then the second step we do imine reduction. Imine reduction is quite common. We did that for reductive amination back in the previous, we talked about that previously. But this is unusual. This is overall an unusual process. And what I mean by that is taking this amide and reacting it with an H- reducing agent and getting not the alcohol, but instead getting the amine. So this alcohol is not formed. Now you're probably asking yourself, well, Willoughby, why would the alcohol be formed? And so that gets to a reduction of other carboxylic acids. So often, or carboxylic acid derivatives, often reduction of carboxylic acid derivatives gives the alcohol. Okay, let's look at an example of that. The only time that people ever do this productively, I've seen it occasionally with acid halides and a little bit more often with anhydrides, but for the most part, people do this with esters, is we could add H- to an ester, and the H- is going to participate in an addition elimination reaction like we just saw, where we're going to add now here's the thing, the O- can now come down and kick out O-. This is a favorable process. Previously, that wasn't favorable because we would have to kick out nitrogen. Nitrogen's not that good of a leaving group under normal conditions. So the oxygen serves as a good leaving group. That's going to give us an aldehyde in this case. Previously, with amides, we formed imines. Here we're forming an aldehyde. And an aldehyde can react with an H- to form another tetrahedral intermediate, but this tetrahedral intermediate gets dealt with through an H+ workup, and this is just carbonyl reduction that we saw previously. Sorry for that hitch in that arrow. Negative charge grabs the H+, and we get our alcohol. Okay, so what happened here? What happened here is that we took a carboxylic acid derivative that was different from an amide, and we did the reduction, we got an alcohol out. And that's because the addition elimination sequence led us to kick out a better leaving group than a nitrogen. The nitrogen species that we saw with the amide stays put, and rather the oxygen looks for an opportunity to leave, usually by adducting with a Lewis acidic group 3 element like aluminum. That allows it to get promoted to leave, and if the oxygen leaves and the nitrogen stays put to make an imine, the imine doesn't last long, it gets reduced. Conversely, with an ester or any other carboxylic acid derivative that is less reactive than an amide, or more reactive than an amide, we're going to do the addition elimination, but this time we're going to eliminate that carboxylic acid derivative group. The weakest of the leaving groups still leaves, and that's the weakest of the leaving groups in this case would be an OR group, and that still leaves. A chloride would leave, an acetate would leave if you had an anhydride, or a carboxylate would leave. These would all be fine leaving groups and better than a nitrogen atom, giving rise to the alcohol product. And so that's why this reaction or reduction of an amide is much more distinct than the reduction of a carboxylic acid derivative. Okay, the other reactions, I'll just mention this once. If you treat, just to re-emphasize one of my favorite reactions, we've talked about this before, but if you treat an amide with something like an acid halide, you can do a cool reaction where the oxygen adds to the acid chloride. Now this is a weird acid chloride. This is oxalochloride. And what I'm doing is, for the sake of avoiding having too many curly arrows in one unit, I'm reproducing a reaction that was central to making acid chlorides. This is called the Vilsmeier reagent. But here we're considering a resonance structure, or we're just kind of considering the fact that, well, we could draw the resonance structure. The negative charge character on the carbonyl oxygen can add to an acid chloride. That can, I forgot the tetrahedral intermediate, goodness me. I can make this species, which can come down to eject chlorine. And we're kind of mixing everything together now. We've got acid chlorides reacting with nucleophiles, and we've got amides reacting as nucleophiles in this one-off case. And then this species can add to what was the carbonyl carbon and push up electrons on the nitrogen. To give us this species, which is now neutral, but it won't stick around for long because we have a thermodynamic driving force where we can remake the carbon-nitrogen double bond, only we're going to break a carbon-oxygen double bond to make a new carbon-oxygen, we can break the carbon-oxygen single bond to make the carbon-oxygen double bond of CO2, push electrons over to make carbon monoxide, and release Cl-. So that gives us this species, which is countered by Cl-, CO2 plus CO. So we've looked at this reaction before, and this is in the synthesis of acid chlorides. So one of my favorite reactions, it shows that amides can be electrophiles sometimes, but for the most part, they're unreactive, and it, even in some cases, can be nucleophiles too. All right. I guess we could always convert amides back to carboxylic acids by treating with water and really strong, really high heat conditions or strongly acidic or basic conditions. I don't want to go through that mechanism because it's not super practical. Usually you have an enzyme or some catalyst do that reaction. Now, speaking of enzymes, in the next lecture, we're going to get into the use of amides and amines and amino acids for the production of proteins. Will serve hopefully as a useful introduction to topics in biochemistry. So until then, I'll see you next time.